that for any two vertices A and X, we have such resistance. And also recall that probability that xn plus 1 equal to x conditioned on your previous step is y. This is omega of xy over omega of x. So y is just A, so the R of effective resistance, inverse of that, is equal to flow of A and B. This is really important. So pay attention that this is just the definition of flow of A and B. Until here, it's just definition. And until here, we are just using that physical law, f of x minus f of a, summation over x, which is adjacent to a. But look, f of a, as I said, is 0. So what remains is that WA summation over x, p starting from a, x1 equal to x. And what remains is f of x. What is f of x? It is probability that t of b is less than t of a, minus. What is f of a? It is 0. So finally, using Markov property, we can say that this is WA, p starting from a, x hits b before its first return to A. So you see how easy this theory of effective resistance is, because we have related the probability of hitting B before it first returned to A to be the inverse or reciprocal of effective resistance between any two nodes that you imagine. So you know that for any two nodes, we know the effective resistance between them. But sometimes we have two sets, B0 and B1. In the future lectures, I will talk about it and see that you can generalize that, so that you can say the effective resistance between B0 and B1, or even, for example, 1 point in a set and different combinations. So all of them are consistent with each other and there is no conflict. So another theorem which is very important is the Rayleigh and Thomson principle. It says that the inverse of your effective resistance between any two nodes or vertices is just the infimum over your Dirichlet energy between two functions f and f with itself, such that f at one side is 0, at the other side is 1. So you see how beautiful this variational approach is related to effective resistance. So it has a meaning when we compute that effective resistance after solving some linear equations, which can be done efficiently nowadays in computer science. So we use this effective resistance when exact calculation is not possible. For example, you have billions of nodes, or it takes a long time, or for some other reasons, because you're doing some qualitative analysis, not just quantitative. For example, in the qualitative theory of dynamical systems, you don't need to just evaluate anything. You have to create some qualitative theorems and concepts so that you use it for more advanced quantitative technology. So the R of effective between A and B, we can write it as the infimum over the omega of x and y, inverse of that, ixy squared. So removing edges increases effective resistance. And what a great theorem is this, that this genius guy Chandra, also Raghavendra, in 1989, when I was 8 years old, on a finite weighted graph, the round trip time, or some people say the commuting time, this is more popular than round trip time. So the commuting time between A and B satisfies this. I think I've talked about this, that if you start from A time to hit B, plus if you start from B time to hit A, is equal to R effective of A and B times mu of omega of V. And another things that you need to know is, Doyle and Snell were those of just pioneers of just describing very complex mathematical ideas for computer scientists. So they were one of the pioneers to say something like effective resistance and those things. Of course, before that, even it goes back to Feller, I think, that these things were first initiated. So let A and B be disjoint, so they don't have any intersection. So if X is not in the union of A and B, then if you start from X, the probability that you hit set A is less than the time to hit B is upper bounded by our effective resistance between X and B, effective resistance between X and A. So you see that effective resistance can bound some relations between heating times of set A and B. So it says that if you start from X, which is not in A union B, which is not there, so the time it takes to hit A, the probability that to hit A, and after that it may hit B, that to hit A is less than to hit B. So there are some events, and sometimes it is the opposite version. So we hit B and then we hit A. So it is upper bounded by the effective resistance between that X and B. Isn't this beautiful? It is so beautiful. Because we are now trying to give some qualitative intuition. So what I want to say is a very important things. And it is called the heat kernel. And in most books, I have seen that they use this notation, Pn of x. And they say transition density. Don't say probability density. It is transition density. And the term density, so it is just a heat kernel, another word for saying heat kernel. And so what is that? It's just the law that you start from x. After n time steps, you hit y. But it is just normalized by mu of y. So because of this, they call it density, transition density. And so we can write, for example, if n is 1, you see that it is your, what you know, that mu x and y, mu x, mu y. So the Laplacian is this. So Laplacian of f of x is 1 over mu of x, mu x and mu xy, f of y minus f of x. And you can write it in terms of this p, f of y minus f of x. As I said, it is just multiplied by mu of y. And what is this? It is just the expected f of x1 minus f of x, because we start from x. So it is deterministic. So what I conclude is that my Laplacian operator here is just another way to say it is a p operator minus I operator. This is really important. I just recall that Dirichlet energy or energy form between f and g, because we use it a lot, at least for using test functions and create some advanced technology, mu x and y, because you might ask, we don't need this because we just solved the Laplacian and using our linear solvers, and why do we talk about these things? And I would reply that, well, you need this very much because f could be any test function, and for any f you get different Dirichlet energy between f and g, and so it shows you how close you are to getting the minimum of energy of f and g. And some, for example, there is a proposition that says if x is adjacent to y, then f of x minus f of y is bounded. It is bounded by mu xy minus 1/2 times Dirichlet energy, f and f. And the proof is very easy. Just use the definition of E and you will see that it's less than that. But I want to say another let's say, proposition that says if f is in L2 and the energy between f and f is less than 2 times L2 norm squared, in particular L2 is in H2, and you know H, when we say H, is that all functions that satisfies the energy between f and f is finite. So the proof is like this. You just write the definition of f of f, and this is just, I'm just writing the definition of that, which is mu x and y. This is upper bounded by f of x squared plus f of y squared mu x and y, which is 2 times f squared. So you see how easy to prove these things. Another proposition which is very important is that if f is in H2, then the Laplacian of f is in L2, and the L2 norm of Laplacian squared is upper bounded by 2 times energy of f and f, and it is upper bounded by 2 times H2 norm of that squared. And the proof is very simple. We just use the definition of Laplacian of f. The norm, what is the norm of that? It's just delta f of x, each one squared times mu of x. So what is this? By definition again, mu x minus 1 times f of y minus f of x mu xy squared. This is less than equal to. summation over x, mu x minus 1. Now just simple inequality that f of y minus f of x squared, this term is just squared, and just use this term, and so what remains is we just need mu x and y times mu x and y, but summation is over y. So this is equal to summation over x, summation over y, f of y minus f of x squared mu xy, which is 2 times energy of f and f. So we have proved it. So you see how easy these proofs are. Oh, and the Kilt process is my favorite. So tau a is the time of the first exit time from A. For example, the first time that we exit, for example, the random box goes here, and then here it exits and goes out. Another time we start from that, again we start from that, and then we go at we stop here. Another time it may exit at this time. Another time it may exit at this time. Another time the random walk might exit at this time. So this is the first time that it exits from that. So we can set your hit kernel x and y, mu y inverse of that. This is the xn equal to y. So in time, and after n time steps, it is we hit y, and n is less than tau I. So at n we hit y, but it is less than the exit time. What is the probability of that? And PA of f of x. So we are just trying to extend it to from Pn to Pna. So we are trying to generalize this concept of hit kernel. So easy computation, easy observation, you will see that all of them are just the same things. So f of y, mu of y, and so again delta is p minus a minus I. So even if you restrict to a, again your operator doesn't change. So it's obvious. So all of these things are just elementary things. They're very obvious. So f of x n is less than time to exit a, time to exit set a. And this is just summation over y. This is just the probability that you need, and because that's expectation, I just multiplied by f of y times mu of y. And another important lemma that you should use is that p of x and y is just Pn a x and z p1, because n and 1, a z and y mu of z, and this is just z over a. Here z over all vertices, but now it's just a subset of vertices. Pn a x and z, p of z and y mu of z. So all of them you can generalize to the restriction case as well. So to prove this, we just use the definition as usual. Xn plus 1 is equal to y, and time to exit a is n plus 1 is still less than time to exit a. And so what is this probability law?